Okay, now we're going to take a look at goodness of fit, hypothesis tests of goodness of fit. And the goodness of fit test is used to test the hypothesis that some observed frequency distribution fits some claimed distribution or a distribution from the past. Here's our notation. Capital O represents the observed frequency of an outcome. And that observed frequency, that means the frequencies from a new sample. The E, capital E, is the expected frequency, and that's what we expect we should have. And the example I used in class was with a grade distribution. I think actually your question on the take-home involves a grade distribution. And I said that if, for instance, for many semesters I had had all my classes, all my statistics classes have, let's say, 20% B's, then if I have 50 statistics students this semester, then I expect 20% of those 50, or 10, to have A's. That's 0.20 times 50. And then little k represents the number of different categories. So for grades A, B, C, D, F, that's 5 different categories. And n is the total number of trials, or the sample size is another way to think of that. So that in the scenario I was just mentioning, the 50 students, that's 50 is n. That's the number of trials, the number of students, the number of grades. All these requirements are met for our take-home, so we don't have to concern ourselves with that. And here's both the hypothesis test and, or the hypotheses rather, and the test statistic. These are always going to be the same, at least for us. The null hypothesis is that the frequency counts, that is the new distribution, agrees with the claimed distribution or the prior distribution that we have seen historically. H sub 1, the alternative hypothesis, is the complement of that, which is that the counts do not agree. So that's very simple, and you don't have to worry about assessing what the null is and what the alternative is. And then below that is the formula for the test statistic, which is a chi-squared. And what this notation means is that we subtract each corresponding expected frequency from the observed, and then we square that, which of course is going to give us a positive value, and then we divide that by that corresponding expected frequency. We do that for each one of the observed and expected pairs, and then the capital sigma here says we add all those up. That will give us our test statistic, which we will calculate for our example here in a moment. Critical values, now we're not going to worry about p-values because I haven't covered that in this class. Critical values are found in table A4, the chi-square distribution, and we use k minus 1 degrees of freedom. K is the number of categories, not the sample size. So we have 5 grades, 5 minus 1 is 4, so we will use 4 degrees of freedom. And not the sample size, not the 50 students. And goodness of fit hypothesis tests are always right-tailed. We don't have to worry about, gee, is this a left tail, a right tail, a two-tail? Goodness of fit hypothesis tests are always right-tailed. Now, we need to calculate, although it's a very simple calculation, we need to calculate all the expected frequencies. We don't use this formula up here in the upper part. That's what we use if all of our expected frequencies are going to be assumed equal. What we're going to use is this formula down here, because all of our expected frequencies are assumed not equal. And a close agreement between the observed and expected lead to a small value of the chi-square, and a large disagreement leads to a large value of the chi-square. And a large enough value of the chi-square causes a rejection of the null hypothesis. And here's sort of a summary of that, particularly in this graph and this graph. If your observed and expected are close together, you have a small test statistic, and so that's going to be down here at this end under the fail to reject region. If you have a large test statistic, that's going to be over here under the critical or rejection region. So here we fail to reject the null, here we reject the null, and the result in our conclusion is that this shows a good fit with the assumed distribution. This shows that there's not a good fit. So here's our example. We're going to consider a sample of 100 M&M candies. So Mars Incorporated, the candy company that makes M&M plain candies, says that they package their candies with 30% red, 20% orange, 14% yellow, 16% green, 24% blue, and 13% brown. That's how they say the frequency of their candies, or relative frequency of their candies, is distributed. Now, it's very convenient that we are considering a sample of 100 candies, but in the problem on your take-home, and the question on your take-home, you don't have such a convenient number. We still use the same formula that we'll see in a minute. But we have a sample of 100 candies, and the counts that we get for each of the colors is going to be summarized on the next slide. We are told here to test the claim excuse me, using a significance level of alpha equals 0.05. So our alpha, our significance level, is 0.05. So here's those observed frequencies, and we put them into an Excel spreadsheet, which I will show you in just a minute. And so here's what we got. We took our 100 candies and counted 13 red, 25 orange, and etc., as you see here. And now we go through the steps of our hypothesis test. So steps 1, 2, and 3 are simply that the null is frequency accounts agree, and the alternative is they do not agree. This would normally mean that we would have a two-tailed test, but we have a right-tailed test because goodness of fit tests are always right-tailed. And as I said before, we're using a significance level of alpha equals 0.05. And here's how we calculate our expected frequencies. 13% as a decimal is 0.13. We multiply that times the sample size. The sample size is 100 in this case, but it might be 72 or 26 or whatever it is for the grades on the question on your take-home. You multiply, though, that sample size times that expected proportion to find out how many candies we would expect to see, how many red candies we would expect to see in that sample. And we do the same thing for the orange. 20% is 0.2, 14% is 0.14 for the yellow, 16% is 0.16 for the green, and so on. Now here's here's a table showing all of the values and the calculations that we would make. Our observed frequencies are again, those are the frequencies that we got from our sample, and they match that table that we saw before. And here are the expected frequencies, which match the frequencies from the prior slide. And what we do is, as the formula shows, we subtract E from O. So we subtract the expected of 13 here from the observed of 13 here. That gives us 0. And then in this cell, we square whatever's in this cell. Whatever's here, we square here. And then we divide this cell, the O minus E squared, by the corresponding E. So that one's kind of unexciting. It's just a bunch of zeros. Let's look at the second row. Our observed is 25, and so we subtract 20, and we get 5, and so that's our O minus E for this color, orange. Then we square that 5, and we get 25. Square it, and we get 25. Then we divide that by its corresponding expected frequency, which is 20, and that's 1.25. We perform similar calculations for the yellow, green, blue, and brown colors. And when we're done with these, then we add all of these up. So you can see how O minus E squared divided by E is what we have here in the formula. And the sigma means add them all up, and they all add up to about 6.682. So that is our test statistic. Now, to find our critical value, in this case, we have 6 colors of candies. So our degrees of freedom equals 5. 6 minus 1 is 5. And we're running a right-tailed test, so the area in the right tail is 0.05. And so we use row 5 for the degrees of freedom of 5. And the 0.05 column of the chi-squared to find our test statistic of 11.071. And now we locate and label our critical value on our chi-square distribution. It's right here, 11.071. Then we locate and label our test statistic. Our test statistic is 6.682, and I don't know really if this is to scale or not. It just was convenient with the font size that I used, but it's definitely to the left of 11.071, and so because we see that this test statistic is below the fail to reject region, then we fail to reject the null hypothesis, and to write our conclusion we go to the flowchart that we've used before for this purpose. Does the original claim contain the condition of equality? Yes, it does, because in a goodness of fit, the claim is always that the new distribution will fit with the old. And then we are asked, do we reject the null? Well, no, we fail to reject the null. And so the wording of our conclusion is there is not sufficient evidence to reject the claim that the distribution is as Mars claims it is.